Hi and welcome back. Today we are going to take a look at this aircraft indicator. I have this one in my stock since a long time. This is the N2 indicator. It indicates the percentage of rotation of the high pressure turbine. A knob is missing here. This unit was manufactured in 1978. This thing was manufactured by AirSearch. Power supply 28 volts DC. And here there is a connector with 10 pins. I don't know in which aircraft this thing was installed. First I will do a teardown of this unit, and as usual I will try to make it work, probably after reverse engineering. This unit is similar to other instruments I have already described. We have this one inter-turbine temperature indicator, episode number 409, and also this one, episode 411. This one is a fuel flow indicator. The servo mechanism is identical, and the servo control board is also the same. This is the schematic of the servo control board. The servo control amplifier is here, so the motor is between the virtual ground here and this point. There is a gain of 154. We can see the DC motor here. This is the gear train, and we have here the feedback potentiometer. And here we have the front end board. The input is normally a square wave, and the frequency is converted into a DC voltage by this board. It is normally a pulse generator. We can see this silvered mica capacitor. This capacitor is used for the generation of the pulse probably, and the average voltage as the output is proportional to the input frequency. Okay, so we can see here 74,121. This is monostable. There is here an LH1987. This capacitor should be connected to this monostable. Bingo. And here there is another LH1987, so I think this is an op-amp. And here we have other transistors. You can see that we have military parts, Jan TX prefix. I will do the reverse engineering of this board. It is not very complicated. It will take 1 hour or so, and after that I will make it work. Okay, so after 1 hour approximately, I have finished the reverse engineering. You can see here the schematic. We have 2 inputs here, so this is the comparator, and at the output we have a square wave, and we need to convert the frequency of that signal into a DC voltage. The signal is fed to this monostable, which permits to have at the output here a pulse with a known duration. The duration of this pulse is defined by this RC network. This RC network should be stable. This is why this capacitor is a silvered mica capacitor. The output is fed to this circuit, which is actually a switch. These transistors turn on or off successively. When the output here is at high level, this transistor is on, this one is off. And when the output is at low level, this transistor is on and this one is off. And there is a pull-up here, because in order to turn on this transistor, we need here a voltage above VCC. Okay, so these 2 resistors are calculated in order to have on that point a voltage above VCC for high level and below VCC for low level. We have here 2 acceleration capacitors, this one and this one. We have here a Zener diode. Therefore, on that line, we have rectangular signal, which is either this voltage, which is the negative rail, otherwise we have this voltage. And this voltage is also used for the feedback potentiometer. We have a ratiometric system, and we can see that we have here a filter, and at the output there is a DC voltage which is proportional to the input frequency, and we have here a 5 volts power supply for the monostable and the pull-ups here. This thing doesn't work. You can hear the motor running, but the pointer doesn't move. Actually, we have the same issue than the previous unit. This cylinder stuff in the middle is not a gear train, but it is actually a friction coupler. In the previous instrument, there was an issue with this friction coupler. So I think that we have exactly the same issue here. We can see here this friction coupler, the multi-turn feedback potentiometer, and the DC motor here. We can see one side of this friction coupler. This one is linked to the motor. The other side of the coupler is here. You can see that there is an O-ring inside. In the previous instrument, this O-ring was a little bit tired. I will add a heat shrink tube here in order to increase a little bit the diameter of this part. This instrument is repaired. Currently the input frequency is 400 Hz, 1 kHz, 2, 3, 4, 5, 6, 7, 8 kHz, 9, 10, 11, 12. Minimum frequency is 200 Hz. That's all for this instrument. Thank you for watching and see you next time for another video. Bye bye.